This is the last lecture, the second half of section 1.4, image encoding. So this is the second part of a two-part lecture here. So I finished off the first one as I begin with this topic of spatial encoding. And I've sort of previewed this a little bit. How we do general imaging is we have these three things: slice selection, frequency encoding, and phase encoding. These all use the basis of gradients, and I'm going to go in these in a little more detail here and then talk about K-space. So I'm going to start here with this diagram, which I like to use for this kind of thing. This is a diagram of a pulse sequence, and this is sort of a schematic of how we do the overall acquiring. And let me point out a couple features that we see here as we walk through this. So in this pulse sequence, you'll recognize already this slice selection here. So I have an RF pulse being played while I'm playing a slice here, and I have my gradient refocusing lobe. And we'll imagine that this is a sagittal slice, so it's cutting through the center of the head, so I can select one little chunk through, in the I guess it would mean the right-left direction, the X direction, to make a sagittal image like this. So I'm exciting the head this direction. And then I've got a couple things down here. This is the phase encoding axis here, where I've got little gradient lobes like this, and this is the readout direction. This really, if you look, you might recognize this as a simple gradient echo that we just talked about. So we have an excitation up here, and then we cause a dephasing first and a rephasing, which is going to cause that echo to form right in the center there, and you can kind of see that in the signal. And then this is the signal we're going to actually measure. And then we repeat this readout each time we measure the sample. So the way we actually do acquire a sequence like this is we acquire this in lines. So if in this very simple example I'm trying to make, let's go backwards. Let's just pretend that's a 16 by 16 image. I'm going to fill up a grid which is 16 by 16. And the way I do it is I do one excitation like this, and I play out all these gradients, and I make these measurements. 16 measurements here during my ADC sampling, and I take the values I measure at those points in time, complex values, and I put it into this table. Those first rows, the top row of that table here. Then I repeat that whole sequence here, and I do it again. This time the only change, everything's identical except for I've reduced the phase encoding gradient a slight bit here. You can see the slight height difference there. So I play it out again, I play these gradients out, I make this set of measurements, and now this is the second row in that table. Because this direction is the phase encode, so I have a slightly different phase encoding in that direction. And this is the frequency encoding, which we'll talk about a little more in a sec. So I keep going through and I fill out this whole table, and this table is essentially K-space. So this is the Fourier representation of the object. And if you apply a two-dimensional Fourier transform to that data, directly the measured sample here, you get an image like this. So this is the bare bones way that we do basic image acquisition and reconstruction. And I'm going to talk about these a little bit more as we get through here. A couple points about the sequences here. So I'm now talking about not X, Y, and Z, but slice, phase, and readout directions. There are three orthogonal directions. They could be X, Y, and Z. In this particular case, how I have this drawn. This is an X slice because it's in the right-left direction. I have my readout being this direction, and so that's AP, so that would normally be Y. And then my readout is a Z direction. So this is X, Y, and Z in this particular example. But we often describe our sequences in logical coordinates. So if I want to take an axial or a coronal image, I keep the sequence looking the same. I just rotate everything so these are on the magnet X, Y, and Z coordinates different. So you often work in these logical coordinates, slice, phase, and readout coordinate sets. I also want to point out, as I mentioned that gradients can be treated orthogonally. So this slice select process here, I have to put this refocusing gradient here to fix the gradient dephasing in the second half of the RF pulse. I'm playing that at the same time I'm putting on the phase encoding gradient and the readout pre-phasing gradient here in this direction. You can play these things overlapping. As long as you're just adding encoding. You can't do that during the readout, otherwise you'll be reading in a different direction. You can't do it during slice, otherwise you'll be selecting a different slice. But these things where you're just adding phase accumulation or changing the phase state of the system, you can do them simultaneously. Okay, so let's jump in on the readout or frequency encoding axis a little bit. So we can think of this a couple different ways. This is a type of experiment very much like the FID experiment. We have a 90-degree excitation and we put a gradient on right away. We don't typically do this. If you're going to do anything, you typically do it with a causing a gradient echo. So you do a 90, you dephase it and refocus to make an echo right here. And you do that so you can actually get a nice symmetric signal through there. But let's actually just look at this example for the concept of what I want to show you about frequency encoding right now. So if I did this excitation, now everything is immediately after this 90, everything's excited, and if there was no gradient on, you would just have a free induction decay. But when I turn a gradient on, something happens. And let's look here at this example here, yet another example of multiple isochromats. So in this example, I have an object, and I picked a tapered object, so it's a little bigger over here on this side than on this side, but it's a continuous object. But what I'm going to do for this example, is to track the signal coming from isochromat A and isochromat B, and I'm going to assume inside they're perfectly homogeneous. But after I've excited, and look at this pulse sequence, after I've done this 90 degree, the whole thing is excited and uniformly, and then I turn on the gradient, and that's this gradient here. So when I turn this gradient on, because there are different points in space, the signal in sample B is going to have a higher frequency than the signal in sample A. So this is the frequency and frequency encoding. B is running at a higher frequency than A while that gradient is on and during this reading period. Let's look at what that does to the signal. So if I were to look at the signals from these guys, the signal from A is, let's just say it's this. It's an exponentially decaying sinusoid. This is its T2 value up here, and the frequency is the oscillation you see is this offset here, this omega A. And the signal from B, I said, is at a higher frequency. I also note the way I did it is that the B magnitude is a little smaller. So A has an amplitude of 1, B is a little smaller, so it has an amplitude of 0.6. But it has a higher frequency, so you get this kind of signal. And let me point out again that the signal I'm showing you is a trace. It's actually a complex signal. So this is the real component of a complex oscillating exponentially decaying sinusoid. So in the real world, when I have a coil and I'm measuring this sample, I have a coil near there to pick up the signal, I'm getting a linear combination of the signal that's induced by each of these isochromats. In the same way, I could simply add to a linear combination of those two signals, and this is the net signal from A to B. And what do you get? You get a complex sinusoid. You've got a beat frequency, so you've got aspects of both of those frequencies combined together, and the decay to be a combination of both of them together. So if I take this data and do a Fourier transform on that, what do you get? You get a Fourier transform does actually, you can think of it as a spectral analysis of this. You would get two delta functions. Actually, since they're decaying, they wouldn't be delta functions. They might be Lorentzian line widths. But let's pretend they're delta functions. They're pretty close to that. You would get the decomposition of this signal is a large component with frequency A and a slightly smaller component at frequency B. So they'd get these two deltas here. And so as we're thinking about, so what we did here is we only looked at those two pieces. If we did the same thought experiment with not just two pieces, but a continuum of all the stuff in this tapered object, you would measure, and you got all those little components together and looked at their complex sum. When you do the Fourier transform, you would produce this, which is a projection of the object in the x direction, the total combination of everything here. And it's really because when I have the readout gradient on, these different parts resonate at different frequencies, and we measure it, and we decompose the signal. We do a Fourier transform to identify what their frequencies are, and their frequencies are linearly related to their position in space, so we recover the whole shape of the object by doing the Fourier transform. This is the essence of frequency encoding. Yeah, I don't want to go, and I'm going to put all these equations up and not have to jump into here too much, I think. Yeah, I think I'll just leave these up here for now. Well, yeah, let's just leave these up here for now, and we'll skip to the next piece here without going too far. I'm already running a little long for the lectures today, I would say. Here's a little detail on what we do with frequency encoding. Oh my goodness. Thank goodness I made that. Okay, so this is the readout component where we have a readout dephasing gradient first to sort of cause a phase. I like to think of it as a wind-up before a pitch, but you're causing a dephasing, and then you rephase it back so you get a nice echo in the middle of this. And so this is your readout gradient strength. And when you turn your ADC, your analog to digital converter on, you sample discretely like this. The total sampling time we often say is TS, and here's the number of sampled points. The time between these spots is the dwell time, a delta T. And that's an important time value here, because it's the inverse of the readout bandwidth, which comes into play in a lot of acquisitions here. So I'm going to come back, and I want to just sort of want you to also think about that little area between one sample and the next sample. What happens during that period is a little bit of phase is accumulated, and the phase that's accumulated is that little tiny area there, which is the delta K in the readout direction from one step in this direction. So that's a little K area there, which is analogous to what we'll see in phase encoding in a second. So let's come back to this sample here. So we talked about this is that readout shape, the pre-phasing, and then the actual readout with the acquisition here, and we're filling in this table. Let's look at that gradient step now. As I have some gradient on here, and I'm modifying it a little bit. This isn't usually how you see pulse sequences. In fact, if you look at a pulse sequence, you'll often see this diagram here. So I have an RF pulse, my slice selection, and they'll show the readout, but they'll show the phase like a table. And what they really mean is this. They're going to repeat this whole sequence with different values of that phase encoding. Here I'm starting with the negative one, bleep, 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 and increasing until I complete the acquisition. And that's what I showed here in this previous slide. There's going to be 16 different blips, and those correspond to the different rows of this table. So typically, I mean, people don't show this in great detail. They wouldn't necessarily show 16. They would just show an icon like this to make you know that it's something that you're incrementing in a loop as you go around. So, but basically the idea is you just change the phase encode just a little bit between each acquisition. And if you were to look at, zoom out from a big perspective, you would see that the gradient phases that are being played, typically they can go from big to little or little to big or lots of other patterns. But this is going little to big. And at some point they go through zero and they come on out the other side. So this is really going from the high end of the low end of phase encoding to the high end up here. With the phase encoding, the step size, these little deltas here are this delta K PE in the phase encoding direction. One thing I like to think about is this. If you think about, if I had some signal, as I think about the effect of the state of the sample before a phase encoding gradient and after, before it's this arbitrary row of Y. If I look at what happens after I apply this gradient here, the K value is this K phase encode. It's the duration of the pulse times that magnitude and gamma. So the state of the object after having some phase encoding is this. It's e to the I2 pi y gamma GPE tau. And this is, if you put the K back in here, you'll see it's really just a Fourier transform. You take this magnitude here, e to the I2 pi y, and then there's your KPE here. So you can see the Fourier transform relationship that's happening when we apply these gradients to apply this complex sinusoid wrapping up. These are some other terms that we typically use when we're describing phase encoding: number of steps, the maximum gradient strength, and the step size is this delta GPE, which corresponds to this K-space step size, delta KPE here. Next thing I'll skip on for now. I'm not going to go through the equations in great detail, but just as I showed you here, the effect of putting a phase on adds a little phase wrap over here. And that has basically a Fourier transform relationship. And you can see that here, if I'm showing a continuous Fourier transform here, that the signal in K space is related to the PY, the signal in image space, and then this is just the phase encoding on top of it. So it's really a pretty clear Fourier transform pair. And you can just do the Fourier transform to go back and forth between the two. I didn't go into the phase encode equations in detail, but if I go back there and you look at what's happening, both in readout and phase, they effectively look like the same thing. Because they're both causing, even though we talk about frequency encoding as they have different frequencies during the readout period, the equations work out to be they're just both frequency and phase encodes are adding a little bit of phase. And let me point out one aspect that's useful to think of to understand how they work together. If you think about phase encoding, we apply a little phase and measure something after it had that little phase applied. I'm going to go back a few slides here. We do the same thing with frequency encoding. So look at this plot here. The difference between this corner, this point in the upper left corner, and the one right below it is that exact same signal with just a different amount of phase applied to them. And if I go down in this direction, you can just see they're the same signal because the sequences played out the same, except for the only difference was a different amount of phase applied to each one. Now think about in the readout direction. The difference between the first signal and the second signal is the difference between that point and that little point there. And the only thing different between them is, I'm going to go back a slide, is that little phase and that little encoding, that little K step that was put between them. So it really is the same kind of thing. And if you look at K-space, there are some artifacts that are different in read and phase, but the phenomena, the mathematical phenomena, really is the same between these two. And that's why a simple 2D Fourier transform ends up reconstructing the image from there. So the last thing I want to talk about is K-space. So you've seen me use these Ks a few times, Ks in the readout and phase direction. And I want to walk through a regular sequence and show you how that works, how we sort of keep track of where we measure things in K-space. This is a pulse sequence here, and in this example, I separated out just for a little bit of clarity. The readout, I spread the sequence out a little bit so my phase encoding is independent from my readout, so we can actually look at K-space a little more carefully here. So what we're going to do is, as I sort of fill in my K-space in this example, we're going to only look in the phase and readout directions. The slice selection is through plane in K-space. So we only have a two-dimensional K-space, and we assume that the whole object, after we excited a slice, that's all the signal to encode an image is available after that slice selection. And when we start, here's a couple rules for how we figure out where we're going in K-space. After every excitation, we go back to phase equals 0, and that's because your magnetization beforehand, you're only tilting downwards out along the z-axis, so there's no phase in the transverse plane until you excite it. So we're only really tracking the phase of that which got excited by the excitation. If that makes sense. Right. So what we're going to do is we're going to walk through K-space and just look at how the effects and the gradients, and we'll measure the data when we turn our ADC sampling on. I'm not going to talk about spin echoes quite yet. So let's look at the very beginning of an RF pulse, this line here. I do my excitation, and here, at this point in time, I'm right here in the middle of K-space. One last subtle note, you notice, by the way, we're not quite symmetric because we typically use, this is an 8 by 8 grid. We typically use even numbers of grids, so there's usually a little heavy on one side than the other. But we can ignore that for large size grids. So we start here in the very center of K-space, and as I step through this first phase encoding here, I've accumulated a little phase, and so what I'll do is it's a negative gradient here, so I'm going to step down in the K direction, and I went down 1, 2, 3 steps. You can see my little 1, 2, 3s here. I did that very particularly. And so at this point in time, the K, where I am in the K space, is right here. So again, I think I mentioned it earlier, I like to think of K as a description of the phase distribution throughout the whole object. So right here, there was no phase distribution through the object, and now we've added a phase wrap in this direction. Maybe it's a Y direction. And so we've stepped down in K space because we have this spatially encoded phase variation. Now when we go through this one, we're going through a negative lobe in the readout direction. So what we'll do is we'll walk over here. So passing through there takes us negative in the KRO direction. And now we're going to quickly turn around and go positive in the KRO direction. But while we do it, we're going to measure. So we're going to go forward these points in time, and during that readout, we're going to record the values of each of those time points. So we just did our first pass through the pulse, excited, read through, and read out this line of K-space. Now we're going to go through the pulse the second time. And this, it's hard to see with this PDF, I'm afraid, but look very closely at this phase stuff. I'm going to go back to the previous one. I'm doing all 3 of those components, and this next time through, I'm going through only 2 of those. So I'm reducing my phase encoding gradient strength here just a little bit. So I've already measured this row here, and this time I go through, I start after the excitation, I go to K0, and I'm about to step through that phase encoding. Since I've only got 2 blips instead of 3, I only go down 2 rows, and I've stepped here. Now I got to do the same readout procedure. It's exactly the same. I go through this windup, which sends us over here. to this part of K-space, and then I'm going to read forward and sample all those pieces of data and get to this part of the sequence. And I keep doing that, so the next time through I'll go down, or I'll go back here. The next time through I'll go down one step and then read that line. The next time I'll have my phase encode be 0. There will be no phase. And this will be 0, and it'll just go to the left and read to the right. And we keep doing this over and over until we fill out the whole piece of K-space. And if you look at the equations that we have detailed in the other pages up above, the rho xy, which is the signal, the pure signal of the object in the xy direction, is really encoded by 2 phase encode directions, and you can reconstruct and that's your signal. That's your the measured data here, and you can reconstruct it by doing a 2-dimensional Fourier transform, which is really the definition of that equation right there. So that's a quick introduction to K-space. Oh yeah, that's one thing. This analogy, I forgot about this till I saw this written right here. You know, they are two. We think of them as 2 different things. Like frequency encoding is sampling different frequencies, yet phase is the same, is measuring something different, and they really are the same thing. Remember, they're derivatives. So if you think of my analogy to GPS, if you think of phase as position and frequency as velocity, they really are measuring the same thing. If you're walking around and you're walking around K-space, you could be measuring your position as a function of time, and that would be like measuring phase, or you can be measuring your velocity and keeping the history of that and figuring out where you are. And you end up getting the same kind of idea. K-space is a spatial frequency space, and we haven't gone in great details of Fourier transforms, but all the Fourier properties that you may know from before, and we'll cover a little bit later, are present in K-space. So if you have high signal frequencies in K-space that are way out, I'll go back here. If you have high signal out here, those refer to high frequencies in image domain, so high ripples and things. If you have a lot of signal down here, those are going to be low sinusoids that are sort of spread out over the whole image space. And we'll talk about that a little bit more when we get into the next set of slides, I think. So this is a very practical way of thinking of the basic types of images, which will cover most of the stuff we do in this class, I think. If you have nonlinear gradients or other effects, then this formalism really doesn't quite follow through. But for the vast majority of stuff we'll do in this class, NMR in general, this is quite useful. Okay, those are the final set of slides I have on 1.4, and that's it. Thank you for listening.